Welcome, everyone. We're going to take a look at the final law, Newton's third law, oftentimes referred to as action-reaction for its little nickname. But hopefully you recall a bit about Newton's first law, affectionately known as inertia, and then we've got Newton's second law, commonly known as Fermat, and we've got the final law for Newton's motion laws, and this one's often referred to as just action-reaction. So we'll intro it today, we'll get some action-reaction statements, and then that's where we'll call it quits for our intro. So a bit of review. I would hope by now that if I ask you what is a force, that you're just kind of bored to tears of hearing that question, but also you immediately have the thought of, well, it's a push or a pull. And one might think that's a general definition, and that's true. It is a general definition, but force is a general term. So we've gone through several, many examples of forces. We're not going to rehash all that here, but I just want you thinking, all right, force causes acceleration. That's going to be a push or a pull. Now, I bet you've heard the term interaction, where, if we said, hey, someone had an interaction, oftentimes it's kind of got a derogatory connotation to it, where people think that like something bad must have happened if there was an interaction, but not necessarily. We're in physics, and the way we're going to define interaction is you've got an action between some objects where they're each going to exert an equal and opposite force on each other. And in all honesty, that interaction or that action-reaction that we oftentimes refer to as Newton's third law, in a nutshell here, that's about what it deals with, is just having, a mutual action, which means that, both parties were involved. And that equal and opposite is also a pretty important little part there. So I would define Newton's third law as for every action, there is an equal and opposite reaction. And again, we see that equal and opposite. And really what that's in reference to is the force. So the amount and the direction are going to be equal and opposite. The amount of the force equal, the direction that they were applied opposite. So sometimes they'll say, you can't touch something without being touched. And that's true. If right now you're seated, and you might think, well, all right, I'm sitting on my chair. I'm touching my chair. That's true, but your chair is also touching you. So we have an equal and opposite reaction with all interactions. Let's take a quick look at Newton's third law in a bit more detail, and then I'll get into some action-reaction examples with you.
Welcome to the International Space Station. I'm NASA astronaut Mark Vandehei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time, a force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied, according to Newton's third law, by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass. So Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
Okay, so a nice thing that video shows is obviously a good example of action reaction or Newton's third law. It's cool that they could do it in space where it's easily viewed. They also got into the concept of mass, and that's a big factor. But I kind of want to talk about it just on its own on another lecture. But for now, I just want you thinking, all right, well, if Newton's third law is interactions, or we've got these equal and opposite reactions, then that's a good starting point. So we're going to have to practice a little bit here, being able to identify and also like make the action reaction statement. And in order to do that, we've got to have force pairs, which is really just kind of figuring out, all right, well, what objects do we have? And what's the push or the pull, and in what direction? And if that sounds more complicated than it should, I apologize. But let me go through some examples here for you of all an action-reaction force pair is. Here we've got a baseball and a baseball bat. And you can see our little vector arrows there to kind of show us that there's something that appears to be equal, so we got the same length there, and there's something that appears to be opposite there because they're in different directions. So with that being said, if we're just considering this interaction, you know, we've got these two objects that are undergoing the same mutual event, and we consider the interaction then between the baseball bat and the baseball. So the baseball forces the bat to the right. That's going to be my action statement. My reaction has to be equal and opposite. So I would say that the bat forces the ball to the left. And it's really just that simple, right? I had to figure out, okay, what objects are we trying to look at here? And in this case, it was the baseball and the baseball bat. Then I had to come up with what direction something was applying a force, and then switch it. So really we've got the nouns in the sentence that just kind of switch places when we make these things. So if the baseball forces the bat to the right, the bat forces the baseball to the left. You might also notice that you have to switch the direction, but we just kind of cut and paste where baseball and bat was and made sure that the direction was opposite, and that's all there is to it for these action-reaction pairs. So let's take a look at some other action-reaction statements, and I'll give you an action, and then you need to be able to come up with the reaction statement. So for our first one here, if I said the action statement is an athlete pushes the bar up. So we've got our two objects, right? We've got the athlete, we've got the bar. And then we see that it was, pushed up. We aren't given like a numerical value. Sometimes we will be, but so if we've got the direction of up and our two objects of athlete and bar, we should be able to make a reaction statement. So if you want to try to do it on your own, I'd encourage you to do so. It's all right if you don't get them right out of the gate or the first crack at it, but slowly but surely, I think you'll find these are pretty simple. So my reaction statement to this action is the bar pushes down on the athlete. So I kind of flipped the nouns, where I had bar and athlete, and I changed the direction from up to down. And it's just that simple. So that means that while she's pushing on that bar, the bar is pushing down on her. That's our action-reaction statements. So here we've got some bowling, a little bowling taking action here. We got a bowling ball pushes the pins to the right. That's going to be my action statement. So my reaction statement is switch the nouns, bowling ball and pin, change the direction. And we should have the pin pushes the bowling ball to the left. So, like I said, I'll get into the masses later, but you might be thinking, like, how could this be equal and opposite? I see the pins when I go bowling, they go flying everywhere, and the bowling ball just kind of keeps on rolling and it doesn't seem to affect it. Mass does end up playing a big role in this, and I would just encourage you not to. I'd like you to think about it, but don't overthink it just yet, because I promise there's a few other little caveats we've got to cover. Right now, we're just trying to get our action-reaction statements. So let's look at one more. The action statement here is the balloon wall pushes compressed air inward. So what's my objects? I got a balloon and I got the air. And the balloon's pushing the air inward. So for my reaction statement, I can switch the nouns, the person, place, or thing, right? My balloon and air. And then I change the direction because it's going to be equal and opposite. So this would be, for my reaction statement, the compressed air pushes the balloon outward. And it's just that simple. So Newton's law, affectionately referred to as, Newton's third law, affectionately referred to as action-reaction. What we're going to see is that equal and opposite. You want to make sure that you can keep that straight from the beginning. Next time when we talk about Newton's third law, I want to factor in masses. And then ultimately, we'll kind of bring this chapter to a close where we get into canceling statements. But we're not there yet. If you find that you have questions on any of this covered, please don't hesitate to ask. Till we meet again, take care.